Okay, hi everybody. So the first reaction we're going to do is going to involve some potassium chlorate today. And what we're going to do with our potassium chlorate is we're going to melt it using a Bunsen burner. So I'm actually going to light myself the Bunsen burner. So let me go ahead and show you the Bunsen burner. And we're going to go ahead and get that started. Hopefully it will light like I expect. Okay, we're going to pause it until I can get this thing lit. Okay, you might be able to see it now. There is our lit Bunsen burner, and we're actually going to use our lit Bunsen burner to melt some potassium chlorate. Potassium chlorate is highly reactive with sugar once it is in the melted form. So I am going to go ahead and I'm going to try to get everything on the screen here. There is my potassium chlorate. I'm trying to get it into and I did not want to do that. Hang on, everybody. All right, so I am melting my potassium chlorate. You can't see very well, but the flame is large enough. I'm going to actually back my flame off a bit so I can bring my Bunsen burner just ever so closer to the potassium chlorate, and the first thing I'm going to need to do is get it to melt. This is one of those situations where even though potassium chlorate is highly reactive in the melted form, it is not very reactive in the solid form, but I am going to go ahead and get it to react, and we are going to test this reactivity in just a moment. It's almost melted, almost all the way melted. Okay. The potassium chlorate is, all right, it is melted at this time, so I'm going to go ahead and turn off my Bunsen burner. Okay, so there is my melted potassium chlorate, and I am going to go ahead and raise this up so now you can see and I want to show you the entire test tube. There it is. There is my potassium chlorate all melted, and to test the fact that it is highly reactive, we are going to go ahead and sacrifice a gummy bear to science. And this is a very old gummy bear because we've had gummy bears be donated to science. And it is a little red gummy bear. There he is, little red gummy bear. And we are going to be able to observe all the energy being given off by the gummy bear. All right, so we have gotten a lot of reaction going on there, and as you can see, it's still giving off a whole bunch of smoke, and the reaction is still occurring. So right now, we have a lot of reaction that has happened. I'm not going to touch that thing because it's super hot, and so at this time, we're going to pause, and we are going to work on the calculations that go along with this. Our next reaction has to do with the burning of a candle. This is a typical candle. It is a tea light sort of candle. And we're going to start by observing the starting mass of the candle. And we'll notice that the starting mass of the candle is going to be represented, and you will need to write this number down, 10.378 grams. Okay. So after we get the starting mass of the candle, then we're going to go ahead and light our candle, and we're going to let it burn for several minutes. And there it is. There we go. Our candle is burning. It's waiting for it to, okay, so, boy, the light is messing with the focusing mechanism of the camera. So we're going to let the candle burn for several minutes, and then we're going to take a final mass to see how many grams of gas are given off by the candle. So we're going to come back to that in a few minutes. We have let the penny, sorry, not the penny, that's our next reaction. We have let the candle burn for approximately 5 minutes. And we're going to go ahead and blow that candle out. And at this time, we are going to go ahead and take a final mass of our candle so we can determine how many grams of gas was emitted. So if you remember, we started with 10.378, and look at that, we came down by a whole 0.1, so 10.278 is our final mass. So when we are looking at this calculation, we are specifically going to be paying attention to the change in the total mass. And if our equation is C25H52 plus O2 yields CO2 plus water, it is both of, let's turn that around, it is both of those gases there that we, so this is going to be a gas here, this is going to be a gas here, that we're going to want to add their total masses together to be able to see what the final outcome is. So for this, then, we can say that we have used up a total of 0.1 gram of the wax. So how many grams of the total gas should we be forming? How many grams of total gas? That means grams of CO2 plus grams of H2O. All right, in this next reaction, we have some sodium hydroxide reacting with some pieces of zinc. And this reaction, as you can see on your paper, forms some sodium zinc oxide, and that is something that can help us reduce the, or actually what we're doing is we're going to add some zinc color to the outside of the penny. So when I put my nice kind of coppery looking penny in here, I am going to get to see a change in my penny, and we want to observe that going on right in there. So I want you to observe what is happening, and in a moment I'm going to pull that penny out of there so you can see what we might be able to perceive as a color change of our penny. So right now it still looks rather orange, and when you put a penny into this mixture, it is undergoing a redox reaction, and it is literally adding a layer of zinc in the form of zinc sodium oxide, sodium zinc oxide. I said it backwards. Are you guys noticing a color change of the penny right now? When I pull it out of there, you are probably going to be able to see it even better. I'm going to put it on my little watch glass next to this so you can see it better. I'm almost ready. I still see a little bit of copper coloring here, but it's almost coated. And let's see here. All right. Can you see that I have turned my penny silver now? Okay, so hi everybody. You'll notice at the top of this page that the word stoichiometry demos is in blue, and that is because I have recorded a YouTube video of me doing each of these 3 chemical reactions for you. This just won't work on my software for me to show you these chemical reactions as I'm doing these calculations, so we're going to have to live with what we have. If you'd like to go watch that video, it is linked here. All right, so to do the calculations having to do with this first chemical reaction, first thing we have to do is be able to balance the chemical reaction. So I need my oxygens to balance first. That means that I'm going to need a 3 here, and I'm going to need a 2 here to get 6 oxygens on each side, but that means that my potassium and chlorine both have to be balanced using a 2 in front of the KCl. All right, so in this problem, we are given 2.8 moles of KClO3, and we are asked for the unknown of how many moles of O2 are there. So I underline both of those because that's going to be really kind of important to us to make sure that we pay attention to it. And let's make sure that for this set of problems, we know that we have the general format of if we are given some type of moles, and we are asked to solve for some other type of moles, that we are going to use the mole ratio of the given mole ratio on the denominator and the unknown mole ratio as the numerator. Okay, so that means that the unknown always goes on top and the given always goes on the bottom. And let's remind everybody that the mole ratio comes from the balanced equation. So those numbers that we use to balance the equation are representative of our mole ratio. And so that when we do that math, it will give us the ultimate result of finding out what the unknown number of moles is for whatever that species that we're solving for. So in this problem, we're given 2.8 moles of KClO3. So that is what I'm going to start with, 2.8 moles of KClO3. And I'm going to go ahead and set that up so that I have put my given mole ratio on the bottom, and that is my given mole ratio is 2 moles of KClO3. So I'm going to go ahead and fill it in just like that. And I'm going to be solving for my how many moles of O2, and that is my unknown, and that means I'm going to solve for 3 moles of O2. Now, the reason why I've set this up like this is so moles of KClO3 can cancel out, and what I'll be left with is moles of O2. My calculation is going to be 2.8 times 3 divided by 2. So when I do that math on my handy dandy calculator, which is sitting right next to me, 2.8 times 3 divided by 2 gives me 4.2, which is 2 significant figures, and that is how I need to write my final answer, 4.2 moles of O2. Okay, so for my next reaction, I might not be using the same unknown and the same given. Let's take a look at what my next calculation is. It says how many moles of KCl will be produced by decomposing 4 moles of KClO3. And so this time, my given is going to be the KClO3, and my unknown is going to be the KCl. And so this one is a little bit easier to do because you're going to see the numbers are going to cancel out as well as the unit labels. So we're going to be given 4 moles of KClO3, and we are going to use our mole ratio again, which was 2 moles of KClO3 and 2 moles of KCl. And you might notice, oh, that means the 2's are going to cancel out, and that's exactly what happens. So we are left with 4 moles of KCl because we also made sure that our moles of KClO3 canceled out as well. So that one was a little bit easier of a calculation, converting from one type of moles to another. Now we have one last calculation in this mole to mole sort of format, and it says if we want to produce 6.5 moles of O2, that's our given, how many moles of KClO3 would be required? So in this case, we're going to start off with 6.5 moles because that is what was given to us of O2. And we are going to use the mole ratio of 3 moles of O2, and we're going to be solving for KClO3, so our unknown will be 2 moles of KClO3. So moles of O2 are going to cancel. Our calculation is going to be 6.5 times 2 divided by 3. So that's ultimately going to be 6.5 times 2 is 13. Divided by 3, and we're going to end up with 4.3 repeating, so 4.3 is going to be our answer here, and the unit label will be moles of KClO3. Okay, so we're going to go ahead and erase that. Go ahead and go on to our next reaction. This is the reaction where we burned the candle wax in the demonstration. You can go ahead and take a look at that if you'd like to. So to be able to do anything with this, we are going to have to be able to balance this equation. So C25H52 is the candle wax, so that means we're going to need to balance the CO2 with a 25. To balance the H's, we're going to need a 26. And to balance the O2, which is with 76 oxygens, we're going to need a 38 right here. So that is pretty big there. So in the demonstration, after 5 minutes of burning a candle, which originally weighed 10.378 grams, it resulted in the use of 0.100 grams of wax, and that's what we're going to go with. The question is how many total grams of gas should be produced? And that terminology should be is actually terminology which means that we are calculating theoretical result, not the actual result, because we saw that if we burned up 0.100 grams of wax, then we obviously released 0.100 grams of gas into the air. But we are looking for how much should be produced, and that's the theoretical amount. So we're going to calculate those. And you'll notice that we are going to have to do two calculations, one for the water and a second calculation for the carbon dioxide, and we're going to have to add those two together. So here we go for the water, and our given amount is going to be 1.00 grams of wax. So, sorry, 0.100 grams of wax, which is C25H52. And we're going to want to do the conversion to be able to solve for grams of the water and the grams of the carbon dioxide. So let's make sure that we have our general format, which is when we are given some form of grams, we are going to use the molar mass of the given to calculate into moles, because that's always equal to moles. So that will be moles of given on the top. Then we'll have the mole ratio of the given on the bottom. And we'll have the mole ratio of the unknown as the numerator. And then finally, our final step in this calculation will be, because we know that 1 mole of anything, including the unknown, is equal to the molar mass, we're going to be able to end with the molar mass of the unknown. And ultimately what that does is it allows us to solve for grams of the unknown. So cool. That means that we can use that format. And so we are going to be starting with the given grams of the wax. And we are going to need to solve for the molar mass of the wax. To do that, we are going to have to do 25. Boy, that really messes up right there. I can't write that stuff right there. I'm going to write it up here. Molar mass of the wax was 25 times 12.01 plus 52 times 1.01. And when we do that, that comes out to 352.77 grams of the C25H52. Cool. So, and the reason again we're using molar mass, if you remember, is that's because it's equal to 1 mole of the C25H52. All right, the next step is we are going to have to solve using the mole ratio, so we can convert now from wax, which, since there's no number here, that's a 1. So 1 mole of the C25H52, and that's going to be equal to what we're solving for, and this time we're solving for the 26 moles of the water. All right, our last step in this calculation will be where we convert from moles of water to the molar mass, which of water is 18.02 grams of H2O. And that is where we add together 2 hydrogens and 1 oxygen. So 1.01 plus 1.01 plus 16. That's where we got the 18.2. So our calculation is going to be 0.1 times 26 times 18.02, and the overall that gets divided by 352.77. Okay, so making sure that we do that calculation right, 0.1 times 26 times 18.02, and that is divided by 352.77, and so we end up with 0.133 grams, and we were solving for water for that part. Our next part is we're going to be doing that same set of calculations again, but this time we're going to be starting the same exact way with grams of C25H52, but we are going to be using that to solve for CO2 instead of to solve for water. So our next step will remain exactly the same. We'll still have 1 mole of C25H52. which will still be a molar mass of 352.77 grams of C25H52. And that will get then instead converted to from moles of the wax to moles of the CO2, and that mole ratio is 25. So 25 moles of CO2. And then finally we end up with the final calculation. This time we're going to be doing moles of CO2, which the molar mass of CO2 comes out to 44.02 grams of CO2. And when we do that math, we get 0.312 grams of CO2. And to get that, I did 0.1 times 25 times 44.02 divided by 352.77. Now, to answer this question, we were looking for the total grams of the gas. So 0.133 plus 0.312 gives us 0.445 grams of gas. And so that's our final answer, and that is our theoretical amount. That means if everything did exactly the way it's supposed to, we would have ended up with 0.445 grams of gas. So then the next question is, okay, if that's the case, then what is your percent yield? If we are using the fact that we know that mass cannot be created or destroyed, so 0.100 grams of gas had to have been produced if that's how much if that's how much mass we lost in the reaction. So our percent yield is a pretty straightforward calculation. We're going to use the actual mass of what was produced divided by the theoretical mass of what was produced. Now, theoretical is always the thing we calculate. So it's always the thing we use the stoichiometry to calculate. We're going to, since this is a percentage, we're going to multiply it by 100. So we're going to use 100 grams of gas that was actually produced, and we're going to divide it by the 0.445 grams of gas that we thought was going to be produced theoretically, and multiply by 100. So if I'm not mistaken, we end up with 22.5. Let me just check my work real quick. It is 22.5%. And that is not a very high percent yield. And the reason why is because we had something called partial combustion. And yes, this is burning, so we were burning the candle. Partial combustion means not all of the wax was completely combusted. In fact, some of the wax got left behind as bits of carbon. So we had partial combustion going on, and we only got about 22.5% of actual result. Okay, we will move on to our final calculation right now. And in our final calculation, this is where in the demonstration I turned the penny from a copper color to a silver color. And so with that reaction, we were actually making some sodium zinc oxide, and that is the stuff that was being added to the penny. So when we do this, we have to make sure that, again, we have a balanced equation, and to balance it, we ended up needing a 2 in front of your NaOH. That means that there are assumed to be 1s in all of these other spots. Now let me remind you here that when we are given grams of some species in the chemical reaction, that we are going to use the molar mass of the given, because that is always equal to 1 mole. And we are going to use the mole ratio of the given as the denominator, and the mole ratio of the unknown as the numerator. And then finally, we are going to remember that 1 mole of anything, including the unknown value, is equal to its molar mass, and that will give us the final result if we are looking for grams as a final result. what if we are not looking for grams as the final result? What if, like in question number 1, it asks us just for how many moles of NaOH? If we are given 5 grams of Na2ZnO2, that means that ultimately what it's asking us to do is stop our calculation before we get to this last step. So that's what we're going to do in this part. We are going to do a grams to moles problem. So in this part, we are given 5.0 grams of Na2ZnO2, and we are going to solve for moles of NaOH. That means that we are going to have to solve for, we're going to have to use the molar mass of Na2ZnO2, and so molar mass is going to be gotten by taking 2 times 22.99 plus zinc's mass, which is 65.38, plus oxygen's mass, which is 2 times 16. So we add all that up, and that's what I'm doing right now. 2 times 22.99 plus 65.38 plus 2 times 16. And that gives me a molar mass of 143.36 grams of Na2ZnO2. And we use molar mass again because molar mass is always equal to 1 mole. So that's going to be our way to convert to the moles. And then we're going to use the mole ratio of 1 mole of Na2ZnO2. And I got that from right here in my balanced equation. We're going to convert to moles of NaOH using mole ratio from the balanced equation of the NaOH. So I've got that. And then the final step I do not need because we just need to solve for moles of NaOH. So my calculation is going to be 5.0 times 2 divided by 143.36. So when I do that math, I get 0.070 after I round correctly, and that's going to be moles of NaOH. Okay, so keeping all of that in mind, that means that I can actually manipulate the mass-to-mass problem to solve for whatever I'd like it to solve for. So let's just see what the next one brings us. And so when we look at the next one, it says if we originally had 6.3 grams of zinc, how many grams of hydrogen gas was produced? So this is just a plain old mass-to-mass or grams-to-grams problem. So I am given 6.3 grams of zinc. And I'm going to use the molar mass of zinc, which is 65.38 grams. I got that directly off of the periodic table. That is equal to 1 mole of zinc. And then I'm going to use the mole ratio of the zinc, which is 1 mole of zinc, to the mole ratio of H2, which is 1 mole of H2 or hydrogen gas. Then finally, I'm going to end up by solving with 1 mole of H2 is equal to the molar mass of H2, which is 2.02 grams of H2. That means my calculation is going to be 6.3 times 2.02 divided by 65.38. And so when I do my math, I get 0.19 grams of H2 as my final answer. All right, we are moving on to the very last part, and this is saying how many moles of NaOH would be needed. So this is asking me for moles of NaOH if we are wanting to produce 4.2 moles of H2. This means we're asking for a mole-to-mole problem. And you might be going, well, hold on a minute. I don't have that skeleton written up here. Let me show you how the mass-to-mass problem skeleton can be used with it for a mole-to-mole problem. If we are not given grams, that means we don't need this section right here where we were given grams and we were canceling grams. And if we are not needing to solve for grams, that means we don't need this section on the end where we are converting back to grams. Instead, we are just going to be given moles and we are going to be using mole ratio. So that is exactly what we are going to do. We are given 4.2 moles of H2, And we are going to use the mole ratio of 1 mole of H2 to 2 moles of NaOH. And that math is going to be 4.2 times 2, which gives me 8.4 moles of NaOH divided by 1, so just 8.4 moles of NaOH. And that's how you can use your mass-to-mass skeleton to pretty much solve for whatever type of problem that you would like. I hope this has been helpful.